Okay, so yesterday we were talking about addressing modes, and we got as far as direct addressing modes. Okay, so just to refresh your memory very briefly, there's three big categories of addressing modes. There's immediate addressing modes when you know the value of the thing you want when you're writing it at assembly time. There's direct when you know the location of what you're talking about at assembly time. And then there's indirect where you know how to calculate, say, where an operand is at assembly time, but you don't know where it's going to be exactly, or you don't know exactly what its value is. So you either know its value, its location, or how to find its value or location. So you use either immediate or direct or indirect. Okay, so we're in the second of those categories now, the direct. We've already looked at how you specify an actual value. Here we're talking about how you specify the location of something. Okay, and there are two broad categories, as I said yesterday. There's register direct and there's memory direct. Remember, the registers are all in the processor. Just remember this about that. Access to items in registers is free. That is to say, it takes no time and uses very little power. Okay? Access to stuff out in memory, though, is costly because it's going to take time to get the thing across the bus, maybe to register. And it's also going to take a lot of energy, a lot more energy than you'd hope to have to use. Okay, now there are four of these variants. There's data register direct and address register direct, which are trivial looking anyway, and then there's two variants of memory direct, absolute memory short and absolute memory long. We'll talk a bit about those just now. Okay, so register direct, that includes address register direct and data register direct. The item that you want is actually in a register. Now, I want you just to keep in mind that what we're saying here is the item is in the register. It's not pointed to by a register, it's actually in the register. So you might be holding something, say, in data register 4, or you might want to put something into data register 4, you'd be using data register direct. You might have something in an address register, like say a number. You might have a number in an address register, you'd be using address register direct to get at that number. You would not. So that's what we're talking about. Now we'll see later that there's a variant called address register indirect, and grammatically it's signified by brackets around the address register when it's specified. Address register indirect, not what we're talking about here. Address register indirect is when you're using the address register as a pointer into memory. Okay, you're using it as a kind of an index. Do you have a question?
Yeah. Does this mean that the registers are in the cache memory?
Does this mean that the registers are in the cache memory? No, not exactly, but the flavor of what you're saying is true. The registers are actually in the processor, just as cache memory is very close to the processor. Access to the registers are not part of any kind of memory at all. They're named places inside the CPU where you can put things. Okay. Once you have things in registers, you can manipulate them. Like say, you can add them or compare them, and so forth. And moving things between registers is very cheap. Okay, basically the cost of the actual move itself is nothing. The cost of fetching the instruction is all you pay. Okay, so having things in registers is very good. But the registers themselves physically are in the chip of the CPU, just typically as cache memory is also on the chip of the CPU. Okay? So it'll become a bit clearer. The thing about cache memory from the point of view that I think you're talking about is you can never actually address a location in cache memory. Okay? You can address a location in real memory, and the mechanism of the computer may take that piece of information and put it in a part of cache memory and then bring it into wherever you specified. But you, the writer of the program, never talk directly about cache memory. Okay, so you can't name them as you can name registers. Any other questions just while we're just talking about that? Okay. So that's register direct, and it's pretty simple, okay? Memory direct is also pretty simple conceptually, okay? And what you're doing is you're specifying the location in memory of the item that you're interested in. And if you have a look at those 2112FA, a hex number there, and there's an expression 6534 minus 21 plus the ASCII code for small a. Okay, those are to be interpreted as locations. Now, if you compare that with what we said for immediate modes, okay, they look kind of similar, don't they? Like if 21, I think 21 was an example I had, and $1048 maybe, or something I had for the example and so forth, and the expression was also quite similar. So what's the difference? What's the difference? The hash sign. Okay, so we're talking syntactically or grammatically, the difference is the hash sign. Remember, the hash sign tells the assembler that what you're talking about here is an immediate operand. The absence of the hash sign is missing here, the absence of the hash sign means that what you're talking about are addresses, they're locations of things, they're memory locations of things. Okay? So grammatically then, the hash sign distinguishes between immediate mode or a direct mode like this. But what's the functional difference? What does it mean? What does it mean? This is very important, and this is a cause of great confusion. So I can understand that you might be a bit reluctant to suggest an answer. But what is the answer? What's the difference? The hash sign is the grammatical sign of the thing, or the grammatical indication of the thing. What's the actual functional difference? So if you wrote down this, okay, what does that mean? What are you talking about then? Talking about the value 27. Thank you very much. So you might say, I want to move the value 27 into D0, right? The value 27. Suppose you wrote down 64 plus the character lowercase a. What would you be talking about then? Yeah, so even though it looks a kind of odd, you're using this as a memory address. So you're saying, okay, take this expression and evaluate it. Okay, so it'll be 64 plus the ASCII code of small a, which is 97, I think. If you look at it as a number, add those together at assembly time. That is when the machine code is being generated. Okay, and so this would then be the memory address at 161 or something like that, whatever it happens to be. Okay? It's a memory location. So the absence of the hash sign means this is a memory location. So the operand is not 64 plus the character a. The operand is what's at location 64 plus lowercase a. And you will get confused about that as time goes by, but just keep your eye on the fact that it's an issue. Okay, so we need to talk, or we're still talking about memory, we're still talking about direct addressing modes, but we need to just actually talk a little bit about the notion of an address space. First of all, if you look at the 68,000, it's a 32-bit computer. Now, saying something is a 32-bit computer is a little bit imprecise, because you can get computers, for example, where the registers where you deal with pieces of data are, say, 16 bits wide, but they have a 32-bit addressing system. Or you can have, nowadays, you might have a computer that has a processor that has, say, 32-bit registers and has a 32-bit address space, which we'll talk about in a moment. But you can also have computers nowadays that have a 64-bit register, so you can manipulate 64-bit quantities, but only has a 32-bit addressing space. So let's just get a little bit precise about it. What we're saying is the 68,000 family, the 68,000 family of processors, the 020, the 00, the 010, the 020, the 030, the 040, and the 060, for all I know, are 32-bit machines, right? And they're 32-bit in the sense that the registers like D0 and A0 and all those, they're 32 bits wide, that's for sure. So if you think about moving information from one part of the processor to another, say from one register to another, not going out on the bus now, those pieces of information are carried on what are called data paths within the chip, okay, within the processor. So the 68,000 has a 32-bit data path internally, okay? So it's a 32-bit system inside. Externally, you're encouraged to think about the 68,000 as having a 32-bit address space. What that means is that an address is a number, okay? So you address, you could have the address, the location 0, the location 1, and so on. And a 32-bit address space is where the number of the address number itself is represented as a 32-bit quantity. Now, if it's a 32-bit quantity, that means that there could be up to 2 to the power of 32 distinct address locations, which is about 4 gigabytes. And you'll see that number appearing, even at the moment, as the upper limit for some processors. You cannot have more than 4 gigabytes of storage in quite a number of machines at the moment. In fact, it's lower for other reasons. 2 gigabytes is typical now. But that comes from the fact that an address number, the index number of a location itself, is stored as a 32-bit quantity. Okay, so the 68,000 can manipulate 32-bit quantities in registers, so it's got 32-bit data paths and registers internally, but also the addresses that you talk about in the 68,000 are themselves 32-bit quantities. Therefore, an address can specify one of 2 to the power 32 different things. Now, to take a counter example, an old processor like the 6800, introduced in 1974, I think, or 75, is essentially an 8-bit machine. So whereas the 68,000 has 32-bit wide registers, the 6800 has 8-bit wide registers, tiny little registers, and there's only 2 of them, A and B they're called, right, and they're called accumulators. And it has so it has 8-bit registers for doing addition and so on, and it's got a 16-bit address space. So the number of locations that you can specify with the 6800 is 2 to the power 16, which is 65,536, 65K. Right? So the 68,000 is far in excess of that at 2 to the power 32, 4 gigabytes of an address space, and it's got all that kind of stuff. Okay, now when the 68,000 itself came out, as I was saying to you yesterday, 64 kilobytes seemed like quite a lot of memory. And so you'd only need actually 16 lines to actually specify, 16 bits and therefore 16 lines to specify any location in the 64K address space. The 68,000 has 24 bits of addressing information that are actually physically used. And if you think 2 to the 24 is about 16 megabytes. So a 68,000 chip physically can reference about 16.8 megabytes, 16 megabytes, strictly speaking, of address space. But you're encouraged to think of addresses themselves as 32-bit quantities, even though the 68,000 itself only uses 24 bits. And actually that caused a problem a few years ago, because if you look at a 32-bit address, which is what you're encouraged to use, only 24 bits are actually used in the 68,000. And so enterprising hackers, benign people now, programmers rather than cracker hackers, they said, oh, okay, we're using a long word to represent an address, but we're only using 3 of the 4 bytes to store information. So why can't we use the other byte for flags and signals of some particular some significance? And that was fine, because while this program that used the upper byte of an address, a 32-bit address, while that ran in the 68,000, the upper byte was ignored. But as soon as you brought that on to another member of the 68,000 family, the 68020, these extra, the signs, the values in this extra byte caused problems. So Apple had to actually bring in a program, RAMME, a sort of a scheme whereby people were encouraged to rewrite their programs so they were said to be 32-bit clean. And we're going back to the late 80s, we're talking about the late 80s, 32-bit clean programs, where programmers who had put information in the upper byte of an address were encouraged to move that information off to somewhere else and allow the program to run on a 32-bit address-based machine like the 6820-based Mac. And there's an echo of that still in the Windows world, is there not? Okay, they talk about clean programs, 32-bit clean programs a bit. Okay, anyway, that's just a historical detail. Right, okay, so slightly complicated. 32-bit addresses really, and you're to think about them as 32-bit. Only 24 bits are used in the 68,000, but that's just a small detail. Okay, so as I was saying again yesterday, there's 2 ways of referencing a memory location in the 68,000. There's 2 sets of hardware, if you like, to do this kind of thing. One is called absolute memory short, and the other is absolute memory long. The difference between them is this. In absolute memory short, even though we're talking about 32-bit address spaces, only 16 bits are allowed to store the address. Okay? If you've got only 16 bits, that means you can only distinguish between 65,536 different things, which means that if you use absolute memory short as your addressing mode, you can only address 64k bytes of memory. And that's a little bit of a restriction. In the late 70s, it didn't sound like much of a restriction. Now it's a very severe imposition. But there's still an advantage to absolute memory short in that an instruction of which its part will be fetched more quickly and therefore will execute it more quickly. So there's absolute memory short and absolute memory long. Absolute memory long is the bog standard one that you'd expect. It's where you can specify any address whatever in the 32-bit address space without restriction. Right? Now, the assembler, you write your program and the assembler converts it into machine code. The assembler, when you write down, say, a location like say, 4073 or something like that, the assembler will work out whether it can use the absolute memory short or absolute memory long variant of it, and will choose short where it knows for sure that it will work. Okay, so the assembler will automatically choose between absolute memory short and absolute memory long. And from what we know so far, it's going to be very straightforward for the assembler to do that. It'll just look at the expression. I mean, clearly that can be, as you'll see, clearly that's an absolute memory short. That qualifies as absolute memory short, so it'll use that variant, and you'll have a slightly quicker instruction as a result. In a fully commercial assembler, you can actually specify, you can tell the assembler to use absolute memory long. You can force it, you can override it and force it to use absolute memory long everywhere or absolute memory short everywhere. Now, using absolute memory short everywhere can cause you problems. Okay, absolute memory long then. It's just what you'd expect. Okay, there's a couple of examples. And just the last point there is that when it comes to encoding the instruction, which has to be encoded in binary, of course, and has to reside in memory itself, the address that you specify using absolute memory long is going to be represented in the instruction as part of the instruction as a 32-bit quantity. Okay, so it's going to take that bit longer to fetch as part of the instruction over absolute memory short. Okay, so here's the thing about absolute memory short. Okay, it's only you've only got 16 bits to store it. So you can specify any address like this, 0000 down as far as F. Okay, they're the values that you can store and that you can represent in 16 bits. Now it gets sign extended. Do you remember we talked about sign extension in a different context the other day? It gets sign extended, and so that means that what will happen is, if you look at it just in 32 bits for a moment, so we'll have the most significant bit here is copied up into the upper word, right? So if it's a bit that's 0, so we've x, 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 we don't care about these, then it'll be all zeros up here. And it turns out that that means in hex 0, 0, 0, 0, 0, 0, 0, 0, up as far as 0, 0, 0, 0, 7, F, F, F. Okay? So that's the first 32k locations in memory, starting at location 0, up as far as location 32,767. Okay? So that's 32k bytes in low memory, as we call it. And then by a similar process, you can show to yourself that the other range is from F, 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 all ones in the upper word, 8, 0, 0, 0, up as far as F, 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 F. Okay, up to all ones. And that's the uppermost, the top of memory. Okay, it's 32k as well. So the first 32k in the memory in the full 32-bit address space, the first 32k and the last 32k can be referenced by absolute memory short. Now you see actually, by the way, again as a side issue, there's an interplay between sign, plus and minus, and unsigned here. You know, we're talking about sign extension here, the mechanical process of copying that bit up. And you can think of it in terms of signed arithmetic on the one hand, but you can also think of it in terms of unsigned address numbers, and you have the lowest 32K and the highest 32K. So we're sort of going between the two worlds, unsigned and signed, to our advantage. So it can be a bit confusing. So if you're trying to write a program to run as quickly as it can, and you have a lot of variables that you want to store, one thing you could think of is trying to store the variables in either the first 32K or the last 32K of memory. Okay, because you have faster access to them there. So it's just something to bear in mind. And again, on other platforms, sometimes that's called the fast page, the fast memory page, relative to the rest of memory. Okay. So again, so now we've had a look at we've had a look at immediate modes, so we know how to specify a value, and we've just looked at direct modes, we know how to specify a location. Now there's one big wrinkle that I want to add to this in a little while, and that's the idea of using labels. We've been talking about memory locations, we've been giving numbers like 21 and so on, all that kind of stuff. It'd be much nicer if we could actually use symbolic labels for those, and the assembler will allow us to do that. Basically, anywhere you can use a number, you can use a label. Now, you can think of a label as, an equate. It's an equivalent. So anywhere you could say, well, anywhere you see the label called foo, put in the value 647. You know, that kind of an equate, a constant, if you like. So we'll have a look at labels in a little while. Any questions? Okay. So now we're going to start talking about the indirect modes. Now we're not going to go through all 5 of them today because it wouldn't make sense. In fact, it's already pretty boring just looking at these damn things, even for me. So for you it must be excruciating. So we're just going to look at one indirect addressing mode to get us going, and we'll add the others as we need them, in writing programs. Okay, so first of all, we have to just think a little bit about addressing modes.